You're bleeding marks in your Cambridge IGCSE physics exams right now, and I can literally guarantee you it has absolutely zero to do with your actual understanding of the concepts. Today, we're fixing that. We're targeting the absolute smallest, most effortless changes you can make to your exam answers to guarantee maximum marks on the 0625 syllabus. We are literally going to stress test your answers against the exact examiner mark schemes until they break, and then rebuild them so they're completely bulletproof.
Okay, picture this. The exam clock is ticking down. The pressure is seriously on. A student is asked to describe what happens when weights are added to a spring, and they write this. The spring stretched because of the weight, right? Seems totally logical. Seems like common sense. But in a Cambridge exam scenario, this exact answer scores a fat 0. No marks. Why? Because it completely ignores the command word fulfillment and the super precise terminology that the examiner is literally hunting for on the page. This is the ultimate tragedy, right? Students know the physics, but they completely fail the vocabulary test. Let's fix that right now.
Let's actually compare two approaches here. On the left, we've got the ordinary, vague revision answer that gets you absolutely nowhere. The spring stretched. Now look at the right side. Contrast that with the exact mark scheme aligned terminology. F equals kx. Force is directly proportional to extension. Do you see the difference? The examiner isn't looking for just some casual observation. They are actively hunting for the underlying mathematical relationship. You've got to stop writing like a casual bystander and start writing like a physicist. If you're just relying on basic, everyday descriptions, your ordinary revision is going to fail you every single time because the mark scheme operates entirely on scientific precision.
So our battleground for this explainer covers some very specific, high-yield zones of the Cambridge syllabus: forces and turning effects, center of gravity, and stretching and compressing. Now, these topics are notorious traps. Honestly, they seem incredibly straightforward when you're just reading the textbook, right? But the second you face an evaluation question or a practical investigation design, the complexity just skyrockets. But here's the good news. By mastering the exam strategy specifically for these chapters, you secure a massive, massive chunk of your overall grade.
So how do we actually construct an answer that the examiner simply cannot ignore? Well, we're going to use this bulletproof 4-step framework that basically forces them to hand over top band marks. Here it is. Step 1, identify the core concept. What is the actual fundamental physics law at play here? Step 2, pull evidence or data directly from the specific scenario or source page. Step 3, apply scientific reasoning to connect that concept to your data. And finally, step 4, the most important one, translate the whole thing into precise examiner wording. Listen, if you filter every single calculation, every explanation, and every description through these 4 steps, you literally remove all the guesswork from your exams.
Now, in just a moment, I'll show you the hidden examiner clue that changes your physics answer completely. But first, you need the framework that makes that exact clue totally obvious. Seriously, clicking away from this explainer right now means missing the exact strategy that turns a borderline passing grade into a guaranteed top band mark. You see, most students just rush into writing without actually decoding what the examiner is secretly asking for. We are going to flip that script entirely so you walk into that exam hall knowing exactly what to look for before you even uncap your pen.
Okay, let's firmly establish our first major concept before we subject it to our intense pressure test: Hooke's law. It states that the extension of a spring is directly proportional to the applied force, provided the limit of proportionality has not been exceeded. This right here is your anchor. But, and this is a big but, just knowing the definition is not enough. You need to know how to deploy it mathematically with the equation F equals kx, where k is your spring constant. This is your foundation, but the actual application is exactly where so many students stumble. Look at how we can transform a deeply flawed calculation into an absolutely unassailable, full-mark response. A totally unprepared student might just vaguely write, spring constant is force and extension, hopelessly crossing their fingers for a pity mark. But by applying our framework, boom, we state the concept, Hooke's law. We provide the evidence by substituting the exact values from the provided data table or graph. We use scientific reasoning by writing out F equals kx and rearranging it for k equals F divided by x. And finally, correct examiner wording by explicitly stating the final substituted values right alongside the correct units. You don't just calculate, you literally prove your work at every single step. All right, let's escalate the stakes a bit here. Everything we've just discussed applies doubly when you're staring down a practical investigation or a data analysis question. Here is a rapid-fire list of the exact traps that catch students out every year. Missing units in your data table headings, rounding your numbers way too early in a multi-step calculation, which completely trashes your final accuracy, giving super vague explanations for anomalies rather than scientifically sound ones, mixing up your independent and dependent variables, and drawing graph axis scales that are just straight up impossible to read accurately. Guys, any one of these mistakes instantly slashes your hard-earned marks, rendering all that theoretical knowledge completely useless. So, we are shifting our focus now to an even harder example, turning effects. To master moments, you absolutely must first master the center of gravity. The definition you have to lock into your brain is this. The center of gravity is the point through which the entire weight of an object appears to act. When Cambridge tests you on stability or, balancing beams, this is the invisible concept dictating every single mathematical interaction. It's basically the pivot point of your entire understanding of forces in equilibrium. Okay, I want you to actively engage with this next one. Seriously, pause and predict. A student is given a force acting on a pivot. They write, moment equals 50 newtons multiplied by 2 meters, which equals 100. Now, the math is perfectly fine, but they lost crucial marks. Can you spot the exact error before I reveal the examiner's correction? Think about what we just discussed regarding precision and completeness. Got it? All right, this brilliantly illustrates the ruthless nature of the examiner's correction. That flawed answer stopped at the naked number 100. But the top band answer, it takes it all the way across the finish line. Moment equals 50 newtons multiplied by 2 meters, which equals 100 newton meters clockwise. The devastating loss of marks came from forgetting two absolutely vital things: the unit, newton meters, and the direction, clockwise. Remember, a moment is a vector-like quantity in terms of its rotational direction. It requires both magnitude with units and a specific direction to be fully correct in the eyes of the Cambridge mark scheme. No exceptions. So to make sure you never fall into these specific traps again, you need to internalize what I call the examiner's secret checklist. Treat this as your absolute safety net for securing those final marks. Number 1, check every single final answer for correct units. Number 2, verify your significant figures actually match the data provided in the question. 3, ensure your graph scales are linear and utilize more than half the page. They hate tiny graphs. 4, always circle and explain anomalies in your data tables. And 5, do a quick check for reasonableness. Does a spring constant of 10,000 newtons per meter make sense for a tiny little slinky? If not, you better recalculate. Let's summarize this entire course strategy with a definitive rule that will help you survive literally any Cambridge question, no matter how ridiculously complex it seems. A strong answer includes correct terminology, substituted values with units, and command word fulfillment. Memorize that quote. Burn it into your mind. When the command word is describe, don't just state. When it's calculate, you must show the substituted values, not just magically produce the final number. When it's evaluate, you have to look at both sides of the data. This is how you play the game by their rules, and it's how you win. But here is the massive, unresolved problem we're still left with. You've fixed your theoretical answers, right? You know your Hooke's law formulas and your moments calculations perfectly. Fantastic. But knowing the answers isn't enough if you completely lack the linked practical or data analysis skills required for paper 6 or the practical components of the exam. What happens when they hand you a totally blank table, a list of messy raw data with varying decimal places, and ask you to plot a gradient to find an unknown weight? If your practical skills aren't as razor sharp as your theoretical knowledge, your grade is still at serious, serious risk. To rebuild those essential practical skills and fully secure your grade, watching the next explainer is your absolute mandatory next step. We're going to tackle the exact data analysis techniques required to turn those practical questions into guaranteed marks. So ask yourself, if an examiner handed you blank graph paper right now, would you survive the practical? Let's make sure you do. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Let's rebuild stronger. I'll see you in the next explainer.